Have you ever gazed up at the night sky and wondered what secrets the stars hold? What are they really made of? And how can something so beautiful also be so incredibly powerful? What happens when they die? Prepare to have your mind blown as we unveil the secret lives of stars. In this video, we'll embark on a cosmic journey to explore the birth, life, and ultimate death of these celestial giants. We'll uncover the mind-bending physics that power them, witness the cataclysmic explosions of supernovas, and even venture into the terrifying depths of black holes. And trust me, you'll want to stick around until the very end, because what happens after a star dies might just change the way you look at the universe forever. Are you ready to unlock the ultimate mystery of the stars? Let's dive in. Before we begin, support Beyond Earth by liking and subscribing. Thanks for exploring the universe with us. Stars are like giant energy factories suspended in space, continuously releasing light and heat. All of this originates from the dramatic and intense energy transformations deep within. Every star in the universe, including our Sun, is essentially a massive nuclear reactor, a dynamic fusion powerhouse. At the core of a star, temperatures reach millions of degrees Celsius. Under such extreme heat and pressure, hydrogen atoms fuse together, triggering violent nuclear fusion reactions. The enormous energy released by nuclear fusion supports the stability of the star, preventing it from collapsing under its own gravity. During this phase, hydrogen is continuously converted, keeping the star in its main sequence stage. This stage occupies most of a star's lifetime, lasting from millions to billions of years. During this period, the brightness, size, and temperature of a star evolve slowly. Our Sun is currently in its main sequence phase and has completed about half of its journey. A star's fuel comes from its internal gas, and its mass determines how fast it burns. Low-mass stars consume fuel slowly, resulting in lower temperatures and dimmer light. Massive stars burn fuel much faster to generate enough energy to counteract their immense gravitational force. Because of this, low-mass stars can live for trillions of years, far longer than the current age of the universe. In contrast, massive stars have much shorter lifespans, often only a few million years. Regardless of its size, every star eventually runs out of fuel. This marks the most dramatic moment in its life cycle, the moment of death. The fate of low-mass stars. Low-mass stars die slowly and peacefully. These stars typically have a mass between 0.8 and 2 times that of the Sun and can live for billions of years. When the hydrogen in their cores is depleted, nuclear fusion stops. However, fusion continues in the outer shell, causing the star to expand rapidly and evolve into a red giant. At this stage, the core contracts and heats up due to gravity, while the outer layers expand and cool. According to scientific predictions, our Sun will enter this phase in about 5 billion years. By then, its size will expand enough to engulf the inner planets, including Earth. As the core temperature rises, heavier elements like carbon and oxygen begin to form. However, in low-mass stars, the temperature is never high enough to fuse heavier elements. Eventually, when the core burns out, the outer layers are ejected into space, leaving behind a white dwarf. During the slow cooling process, white dwarfs emit ultraviolet radiation, illuminating the surrounding gas and forming planetary nebulae, stunning, colorful remnants of their past. This marks a peaceful and beautiful end to a low-mass star's life. The fate of intermediate mass stars. Stars with masses between 2 and 8 times that of the Sun have a more turbulent death. They also go through the red giant phase, but at even higher temperatures. These stars are capable of fusing heavier elements such as oxygen and magnesium. As the core contracts under gravity, the outer layers expand, turning the star into a supergiant. If the star is massive enough, its outer layers become unstable, leading to the ejection of huge amounts of material. Finally, a critical transformation occurs within the core, triggering a supernova explosion. When a supernova explodes, the core collapses rapidly under extreme force. A violent rebound occurs, releasing an immense burst of energy and scattering stellar material across the universe. Supernova are among the most spectacular events in the cosmos. They also play a crucial role in cosmic chemistry. Their explosive force creates and distributes a vast number of chemical elements. Before a supernova explosion, a star mainly produces lighter elements like carbon, oxygen, and silicon. During the explosion, extreme heat and pressure allow for the synthesis of heavier elements, including gold and uranium. The precious metals we see today, such as gold, originate from ancient supernova explosions billions of years ago. The impact of supernova explosions. Supernova not only create new elements, but also release high-energy particles into space. One such particle is cosmic rays, fast-moving, high-energy particles that travel through the universe and even reach Earth. When cosmic rays collide with Earth's atmosphere, they generate secondary particles, such as mesons. These interactions can be detected by specialized equipment, such as the Super Kamiokande in Japan, a massive underground laboratory filled with 50,000 tons of ultra-pure water and over 11,000 photomultiplier tubes. This facility detects faint light signals produced when cosmic rays interact with water molecules. The fate of high-mass stars. For stars more than 8 times the mass of the Sun, their fate is even more extreme. Massive stars burn fuel rapidly, fusing progressively heavier elements until iron forms in the core. However, iron fusion does not release energy, it consumes it. Once a star's core is primarily iron, it can no longer sustain nuclear fusion. At this point, gravity takes over, leading to a catastrophic collapse. In an instant, the core collapses, triggering one of the most powerful explosions in the universe, a Type II supernova. The outer layers of the star are violently expelled into space at speeds of up to 10,000 kilometers per second. During this explosion, the extreme conditions allow elements heavier than iron to form. These newly created elements scatter across the universe, becoming the building blocks of future stars, planets, and even life itself. What remains after a supernova explosion depends on the mass of the original star. If the core's remaining mass is moderate, it becomes a neutron star, one of the densest objects in the universe. A sugar cube-sized piece of neutron star material would weigh as much as a mountain. Neutron stars spin at incredible speeds and emit powerful radiation beams, making them observable as pulsars. If the collapsing core is extremely massive, it continues to shrink indefinitely, forming the most mysterious object in the universe, a black hole. Black holes possess the strongest gravitational force known to science, so powerful that even light cannot escape. They represent the ultimate abyss of the cosmos, where space and time are warped beyond comprehension. Thank you for watching. Don't forget to like, share, and subscribe for more space adventures.